IAA.
Martín, un segundo.
Okay.
Yo voy a comenzar y luego te doy la palabra.
Sí, muy bien, venga.
Okay. Good morning, everybody. Thank you for being here for a new talk here at the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have the talk by Dr. Jesus Toala, and he will talk about destroying planetary systems. Dr. Jesus Toala will be properly introduced by Martín Guerrero. Martín, please.
Okay, thank you, Rene. Well, everybody knows Jesus Toala here at the IAE, but I'd like to provide you all the details about his life and productive career. He got his PhD here in October 2014, and because he ended the PhD in advance of the duration of the grant, we still have money to hire him as postdoc here at the IAA. Then he left on January 2016 and moved to ASEA as a distinguished postdoc fellow there at Taipei in Taiwan. In June 2017, he moved to Mexico, and from then he's investigador asociado of the area, one of the UNAM Institute. He has the SNIE level 1 at this position. He arrived there at area, and he made a new group of stellar evolution, including master students, PhD students, and postdocs. Since his stay there at the area, he has led the work of 2 postdocs. He has got 1 PhD, 3 master theses, and another 3 career theses. At the present, he's got 4 PhD students and 2 master students. And he recently got the Cátedra Investigación para Jóvenes Científicos of the Master of the Marcos Moschinsky in 2020, which provided by the Physics Institute of the UNAM and Foundation Marcos Moschinsky. I have to say that since he's arrived to Mexico in June 2017, he has published almost 50 papers in refereed journals. His expertise include both computational astrophysics and observational astrophysics. In most of the cases, leading with bubbles around evolved stars, including Wolf-Rayet bubbles, planetary nebulae, and nova remnants. And now he's also destroying planetary systems. Your turn, Jesus.
Thank you very much to everyone. I won't be able to see myself on the video, so just feel free to see my face sideways. I will be speaking directly to the people in this room. So whenever you want to stop me, please do so. So I want to start saying thank you to everyone who are here physically and on the Zoom session. I'm really happy to be back in Granada. I always feel welcome whenever I come here. So thank you again to everyone. So today I want to talk about destroying planetary systems. And first of all, I will give you a short introduction on planet formation, which I guess there's plenty of people who are experts at the Institute about this subject. I will go then into the solar-like stars evolutions, including the planetary nebula formation, and then the effects of binary systems, including planets, and then we will go into the vestiges of planetary systems, which is the subject that we are working currently. So you might know that planet formation is and their evolution is directly linked to the formation of stars in the universe. Stars form in star-forming regions, and they are located in this filamentary structures within our galaxy. For example, this is a Herschel image combining the PAX and SPIRE data. So stars form in this filamentary structures. So the star or planet formation has been defined since a few decades ago by Xu, Adams, and Lizano. So what they propose, and which is the still accepted scenario for at least for solar-like stars, is that so the clumps in these filamentary structures, they collapse by gravity, and as a result of angular momentum and different other physical mechanisms, what we have is that we form a disk, and then which fits the protostar, and then we end up with a planetary system. Of course, observations and theory have been improving with the past decades. There's plenty of observational works and theoretical works you can find in the literature. I just wanted to mention, give an example. This is the system AB Aurigae, and this is a work published in 2020. These authors use sphere H-band observations, which you cannot read on the top of here. And this is how the proto-planetary disk is accumulating material to form what will be a planet. And this, of course, can be contrasted with hydrodynamical simulations of gaseous and dust-rich disks around proto-stars. Currently there's plenty of time used to characterize, search, and study these proto-planetary disks. This is just an example of one large project. It's called D-Sharp, and has been done with a VLT NACO instrument in the L-band. So you can see here a large number of morphologies, and what we know, what we think is that planets are forming within this spaces, these burrows between the rings. So this is where planets are being formed. Also, there's lots of time invested in the characterization, the search of planets around mature stars. In particular, NASA announced recently that we passed the 5,000 confirmed planets around main sequence stars. There's more than 8,000 candidates, and which correspond to 3,700 planetary systems. This is by April 20th. And of course, in this webpage, if you have ever been there, you can take a look at the numbers, which are the numerous planets, which you can see are the giant gaseous planets, Neptune-like, super Earth, gas giant, and some terrestrial and unknown planets. The larger planets are easier to detect because of different conditions and the methods we use to detect them. I want to mention that the first planet, actually the first planetary system ever detected, was around this a pulsar, which is the remnants of a massive star, which allegedly exploded as a supernova. It was particularly easy to detect, easy quoting marks, because the authors, what they did is one expects that a pulsar has a very specific time variation. So what these people did is they just subtracted different periodicities from the light curve, and they suggested that different contributions correspond to different planets. And these correspond to 1, 2, 3, and 4 planets. That was in 1992, so which is like 30 years ago. But the first exoplanet around the solar-like star was reported in 1995. So these authors, which you cannot read here, is Meyer and Queloz in 1995. So what they did, they used this at the transit tool to detect a Jupiter-like planet around this solar-like. This is 1.1 solar mass star. And since then, you can go into the literature and find lots of lovely papers reporting the discoveries of planets. This is just the one that I like the most because they have this gift image, and then you can actually see the planets moving around the star. So the star is hidden here behind this coronagraph. So you can actually hide the brightness from the star, and then you see how the planets move around. Like, I think this is a 7 years period of time. The star is HR 8799, and this paper is from 2008. But then we are convinced that solar-like stars evolve and create the most beautiful objects in astronomy, which are the planetary nebulae. And this is just an example of a planetary nebula. This is NGC 2022. This is this year's planetary nebula. And I won't go into the details. If you want, you can ask at the end of the talk, but let me just tell you. So this is the HR diagram of one solar mass star. So we start in the main sequence phase, and then the star runs out of hydrogen in the nucleus, so by different factors. So the star evolves and becomes asymptotic giant branch star, reducing its temperature to something about 3,000 degrees. And then the gravity of the star is decreased, so the mass loss rates, material is lost by the star, and then we have the inner post-AGV object, which starts to increase in its temperature. The ionizing photon flux increases and then creates photoionized nebulae, which are identified as planetary nebulae. Finally, the material just mixes with the ISM, and then we end up with a hot white dwarf. So these are the three main phases I want to concentrate. But of course, there's a lot of physics in between. In particular, during the AGV phase, the star exhibits a very dense and slow wind that creates these magnificent shells. This is CO emission from this AGV star, which is T until A. The size of this shell is about 0.05 parsec, which is 10,000 astronomical units, which is a lot compared, let's say, with our solar system. Then when we enter the post-AGV phase, so the star increases its temperature, so it develops a line-driven wind, which can be as fast as 4,000 kilometers per second with a relatively low mass loss rate. The important thing here is that the ionizing photon flux can be as high as 10 to the 46 photons per second or higher than that. So what you see here in this image is the inner rim, which is produced by the fast stellar wind, and then the outer ionized nebula. This is NGC 6891 image obtained from HST. And the image is the combination of oxygen 3 and H alpha. So all of these effects, the winds, photoionization, shocks, and everything, is what creates the planetary nebulae. And then, as I mentioned, the nebula just expands and then mixes with the ISM, and it's so far away from the star that and the density goes down, so we don't see anymore any hints of a nebula. And then we end up with a white dwarf, a blue object, which I point in here. This is a white dwarf 0005 plus 511, which I will talk about later. So this is a very nice image from ESO, which shows that planetary nebula has a large number of objects which are round and not round. In particular, you can see that most of them have nothing to do with spherical symmetry. So these are examples of non-round planetary nebulae, which are the most dominant planetary nebulae. You can see that most of them exhibit like cone-like symmetry. They're hourglass symmetries, bipolars, jets. So there's a lot of the scenario that I just told you, this win-win interaction, it doesn't hold, or it cannot explain this morphologies. Of course, this is something that has been known for a long time. And the problem now is that even those are very round, or they seem to be round, when looked at a 10-meter telescope, you can start detecting these amazing bipolar flows, which are very fast. This is, in particular, this is the NGC 2359-92, the Lion's Head Nebula. And you can see this very fast 200 kilometers per second jet, which is piercing through the nebula. So even though those that looked round, they're actually not round when looked with better instrumentation. So planetary nebulae shaping has been discussed for years, since the late 80s. And there has been three physical phenomena that have been proposed to explain these morphologies. First of all has been rotation. So what people suggested is that the star has to fast rotate in order to create that the mass flows has to be bipolar. But we know that the required rotation in order to start to produce these jets have to be like larger than the break-in velocity of the star. So this cannot be accounted for. On the other hand, binarity and magnetic fields have been able to explain with simulations the formation of these nebulae. And recently, or more, one of the scenarios that have been taken lots of impetus is the common envelope evolution, which is that when the star enters this AGB phase and inflates its outer envelopes, a companion may enter the atmosphere of the inflated star. So the orbital parameters, they get reduced, and the gravitational energy is transferred into the envelope, and then this produces the bipolar mechanism. There's currently lots of simulations one can find in the literature talking about describing this in binary interactions, which have been directly compared to ALMA observations of proto-planetary nebula. And you can tell that differences are, well, there are almost no differences in between models and observations. This is just an example I found of a common envelope simulation. What we are seeing here is the pole-on simulation. The two stars represent the position of the stars, and you can see that the orbital separation was larger, and then they became closer, and material is being ejected in these spirals or structures that, when looked into the pole edge on, this is the orbital plane view. So you can see that this create these toroidal structures, and then the jets are naturally explained because jets are produced by the escape velocity from the companion. So you see this very nice structures. Again, there's plenty of simulations exploring these effects and on the initial separation, the mass ratio between the companions, the different evolutions. So it's very rich phenomena. But okay, so when the star enters the AGB phase, it inflates its outer layers to more than 300 solar radio, which is something between 1 and 2 astronomical units. So we will have this. So in this particular case, in our solar system, so the sun will consume something about Mars or something like that. We know since a few times ago that so those planets located below something about 1 astronomical unit will be swallowed by the inflation of the star. And those that are farther away from 1 astronomical unit might be spiraling into the star, or they can have the decrease on the gravitational force will make them to migrate to larger distances and probably survive the inflation of the star. Of course, it depends on the mass of the star, the position of the planets in the planetary systems, and different other parameters. But then again, the planets or the planetary system can also have the same effect as a stellar companion into shaping the planetary nebula. This has been explored in recent papers. Well, the results are fascinating because lots of planetary, the central stars of planetary nebulae, some of them seem to be single stars, but with extreme bipolar nebulae, and we still have detected any companions, but of course, we think it's planets also. So the final destinations of these planets, although they survive the evolution of the star, is expected, their final destination is just photoevaporation by the strong photoionizing flux from the white dwarfs. And this is a nice image I found online. So this is a blue white dwarf and a planet being photoevaporated by the strong flux from the star. These are not new ideas, although the simulations have now have the power to start resolving the physics of these systems. But Noam Soker since the 90s have been proposing lots or pushing this idea of the substellar companions shaping or driving the shape of planetary nebulae. We still don't have any clear identification of systems that have planets that have shape in planetary nebulae. We still don't have any confirmation of this. But planets have been found to be guilty of shaping the AGB mass loss from some stars. These are examples detected with ALMA, I think, published in 2020 by the Sun. So what they propose here is that these apparent single stars have these spiral-like structures around them. So they attribute this to the orbital presence of planets. So here in colors, you see the blue shifted CO lines between from the systemic velocity. So you see these very nice structures, and some of them these velocity gradients within the molecular material. And regarding white dwarfs, so in 2021, there's this review written by Veras that reported all of these structures that are present or have been detected by 2021 around white dwarfs. So he reported 4 major planets, 3 minor planets, 60 disks or rings, and about 1,000 planetary debris disks around white dwarfs. In that review, so this is the 4 examples that he presents. So you can see, so this is one white dwarf and a pulsar with a Jupiter-like planet, and a white dwarf, something that he calls evaporating ice gas, dwarf. And this is one of the most complex on the bottom right panel. This is a triple system with a giant Jupiter-like planet. So the point that the author here in this review is trying to make is that probably there's a lot of processes that produce this planetary systems, so white dwarf planet systems. In particular, the more complex here has been argued that went into the common envelope in order to a triple system to have survived. Of course, since 2021 and this year, probably there's a lot of, you cannot see here, but there's plenty of papers that I still searching for planets around white dwarfs and the new identifications of planets around white dwarfs. Okay, so this is what I want to talk about, and we called it the vestiges of planetary systems around white dwarfs. And what we do is that we use X-ray emission in order to look for these planets. And why do we do that? So let me start by saying that X-ray from white dwarfs, hard X-rays, are only attributed to the presence of a binary companion, a stellar companion. White dwarfs have effective temperatures below 10 to the 5 degrees, and they have a negligible contribution to hard X-ray emission to energies above 0.5 kilo electron volts in the X-ray domain. So whenever we see X-ray emission associated to white dwarfs, it is because there's a latent companion which produces coronal emission, or an accretion disk that's been accreted by a close companion. And the story on the hard X-rays from white dwarfs started. This is the planetary nebula called the Ring Nebula. And in 2001, Martin, Yohua, and other people reported that the X-ray emission from the central star of the Helix Nebula exhibit a soft X-ray emission below 0.5, which is the photospheric emission from the star, and then some hard X-ray emission around 1 kilo electron volt. Since then, Yohua started this long-lived project looking for or characterizing the hard X-ray emission from white dwarfs. Until 2010, there were 3 papers published looking for all the observations available from Rosat, XMM Newton, Chandra, and then they study the spectral properties of these stars. These are, I'm showing here just a few examples to start with. So you see they are all more or less different, and they all have a contribution to the hard X-ray emission from this is, I'm highlighting here 0.6 up to 10 electron volts. And these cases, and most of them so far, they have companions which were identified through infrared observations, and in some cases they have accretion disks which are identified through other mechanisms, H-alpha emission lines, for example. But within this sample of hundreds or around 60 white dwarfs, there were some unique cases which were hot white dwarfs with effective temperatures of 200,000 Kelvin, 100,000 Kelvins, with no signatures of a stellar companion, but still strong X-ray emission. In particular, so in 2021, is when I joined this project, which is long-lived, as I mentioned, and we analyzed new XMM Newton data on these three hot white dwarfs. So this is KPD, the one that I've shown you an image before. PG 1159 is one of the most iconic hot white dwarfs in the literature, and white dwarf 0121, which is very similar to PG 1159. The black lines and the dots are the observations and the best fit model. I want to highlight here that I don't know if you can see this solid line at the leftmost edge of this spectrum. This is the contribution from the star. The rest is just hard X-ray emission. So photosphere contribution is just this purple or dark blue line here. In particular, this KPD 005 is the only one that has enough count rates or photons for us to produce a temporal variation analysis. So what we see here is the light curves extracted from the XMM Newton data and the Chandra data in the hard bands from 0.6 up to 3 or 0.7 to 2 kiloelectron volts. So we actually see variation in this. It's evident in the XMM Newton data and the Chandra, which had some instrumental problems, but still there's some hints on this variation. So the temporal variation analysis, we concluded that there's a period of 4.7 hours with a false alarm probability of 1%. So it's a real variation in the hard X-ray emission. Furthermore, and more surprising, is that we also see some spectral variations. Although the spectrum, what we did is we extracted a spectrum in the lower state and the higher state. So you might not see it if you're not familiarized with X-ray data, but there's some contribution. This is a magnesium 11 line, and this is very likely nitrogen 5 line, so we see differences in the spectra with time within a single white dwarf. So this is very interesting, and we still don't know how to explain this. You can ask me what I think later. But then finally, what we were trying to do is we're trying to looking for this companion, or at least a late type companion. Here in black, you see spectra, near infrared spectra from this hot white dwarf. And in black diamonds, these are photometric measurements. So you see the observations. And then we see no bump or no infrared excess, which will be attributed to a companion. So what we did here is to estimate what will be the contribution in the infrared for different stars from M0 to M8. And we practically or virtually see no excess in the infrared. So we propose that a substellar companion might be causing this X-ray emission. In particular, we said it could be an M95, a main sequence stars, a T-type brown dwarf, or a Jupiter-like planet. If we take the period of the variation of the hard X-ray emission, and then we compute separations with using just the simple Kepler laws, and we also estimate the Roche law of each object, only the Jupiter-like planet can fill this Roche lobe and then create this accretion disk onto the white dwarf. And actually, let me just move this. The planet is located something about 1.2 solar radius from the white dwarf, and the Roche-Lobe radius is estimated to be 0.067 solar radius. So it's actually overflowing this Roche-Lobe. If we just estimate that the accretion mass on this white dwarf is something, can be estimated something like this. Sorry, just the windows for the Zoom people. I'm just moving the Zoom windows. The mass accretion of onto the white dwarf is something about 10^14 grams per second, which is enough for a Jupiter-like planet to survive for 10⁸ years, which is very good. It's very nice. And just a reminder, a Jupiter mass is 2 times 10⁻30 grams. But okay, so if planets are contributing to the hard X-ray emission from this white dwarf, so we still don't know how the variability is produced. We think it's because of the orbital motion of the planet, but are there also any similar cases? Or what about magnetic fields? I didn't say so, but in the FITs, we required power law components into the FIT, which might suggest the presence of magnetic fields. So this is when one of my PhD students' PhD thesis started and was born. So there's two goals in his PhD thesis, which is a systematic search of variability in the hard X-ray emission from the satellite archives, and producing the first radiation hydrodynamical simulation for this phenomenon. So I will describe what we have done so far. So first of all, we started by correlating the Villanova University catalog of white dwarfs, which includes more than 14,000 sources, with the XMM Newton catalog. This is just to start. This resulted in more than 100 white dwarfs, which is a total of 7.8 megaseconds, which is 2,100 hours of observations with XMM Newton. However, after rejecting those that have been defined as a binary systems, we end up with 32 white dwarfs, which was good. And this is about 780 hours of observations. Sandino have done a very nice work, and I'm just going to show you some of the results that we have. 9 of these white dwarfs have enough counts in order to study the variability from the hard X-ray bands. These are just examples. You can see that the variability is evident in the systems. And in general, the periods that we can estimate are something about 2 to 15 kiloseconds, which is like half an hour to 4 hours. One interesting result that we have is that, so these are the spectra of the 9 sources. They all are different. They're not similar in any. Some of them might be similar, like this and this to this, but the rest of them, maybe that we don't have enough counts in these cases, but some of them they're intrinsically different, spectroscopically speaking. So this is part of the result. So this is the white dwarf on the left, the number. This is the estimated period, and then just ignore the rest of it. Just have in mind that we propose the same 3 candidates, an M9 main sequence stars, a brown dwarf, and a Jupiter-like. So we also estimated the separations with the period, and then the Roche-Lobe. And then just this is the main result, that the Jupiter-like planets are the ones filling the Roche-Lobe. These are the estimates of on the right bold-faced texts are the estimates of the Roche-Lobe radius, and then this is the radius of the Jupiter, and this is the separation, the estimated separation for the different binaries. So in all cases, they're below the separation, and then some cases might suggest that the brown dwarf can be also accounted for this. But in general, this is the Jupiter-like planets. Interestingly, We also went and look for the infrared emission of these systems. So what we have here is the 6 sources that we found a complete set of infrared data. And I am plotting here the different black body contributions from the stars in blue. And then the rest of the mid-infrared is the contribution from debris disks or clouds. In particular for this, the white dwarf 0121, the one in the middle top panel, we produced a specific cloudy model of this star, and we need the model requires something like an Oort cloud with 100 to 1,000 astronomical units surrounding the star. So our conclusion on this part is that hard X-ray emission is produced by accretion from a Jupiter-like planet, but we also have infrared excess that suggests the presence of debris disks or something like an Oort cloud around the white dwarfs. So this is what we call that we are witnessing the vestiges of planetary systems. We still have some work to do. In particular, we see that although the spectra of the X-ray emission are different within all sources, we seem to have some correlations between the total luminosity, X-ray luminosity, and the hard X-ray emission, which still don't know if it's true or just an artifact. But in particular, we see that if we compare the variation of the period and the luminosities, these 2 sources, which are the less X-ray luminous, are those that are the cooler ones. These are 2 stars with 8,000 degrees of effective temperature. So this might be telling us something on this, but we still require more objects in order to increase our statistics, and we still need to check this correlation. But these are very nice, surprising results. We're still working on it. Finally, so the second part of this project is to develop gravel radiation hydrodynamical simulations where we account for the presence of a white dwarf, hot white dwarfs, and the presence of a Jupiter-like planet. So we can estimate the mass loss rate or the accretion mass onto the white dwarf. We can use those as parameters. We know the masses of the objects, the orbital period, mass accretion rate. So we have all of the ingredients in order to produce our own simulations and explore the physics behind these systems. So I'm going to show you the results of density, temperature, soft X-ray emission, hard X-ray emission, and this is the ball-on simulation of 4 parameters close to the KPD system. And you will see on the density panel, there's a 0 on the top right hand of the panel. Numbers indicate hours in the simulation. So I will play it and I can replay it back again if you have any questions. So we see mass is lost from the giant planet, and then it is gravitationally attracted into the white dwarf, into this spiral density enhancements. And then you can see that X-ray emission is present in something like a disk-like structure that seems to be well contained. The temperature only have the highest temperature, which is the X-ray emitting, is very close to the star. And then this is the edge on of you can more or less see here the planet, and this is the white dwarf. This is the planet, and the white dwarf is here. So this is the edge on. So there's a formation of a disk, and the hottest is the region close to the star, which is the temperature is increased because of viscosity effects. This is something that we're still working on. We need to run different simulations for different parameters, let's say masses or periods, variability periods. But these are promising. These are very promising. And okay, so I'm going to leave you with my final comments. Planets can definitely survive the harsh evolution of produced by the hot stars. The final destination will be to be photo-evaporated from around the hot white dwarfs. And this, my second point here, is a very interesting scenario that I've been Camila has been talking lately, and I haven't got the chance to talk much with her, but which I will be very interesting, is can a second generation of planets form during the common envelope phase, which will be another explanation why we still have planets after this dramatic evolution and dramatic changes in the stellar wind parameters. Planets can produce the same effects as white dwarf stellar companions. They can help shaping the mass laws, and they also produce hard X-ray emission, and they likely to pollute the white dwarf surface. So there's a lot of examples in the literature of people reporting that white dwarf with very unique abundances, which most of the times are attributed to the engulfing of a planet, for example. So what we can conclude from the analysis of the hard X-ray emission is that the combination of the presence of the hard X-ray emission and this infrared excess is what we see as the last vestiges of planetary systems around these white dwarfs. We are yet to understand the configuration of such systems, because if you remember, the planet is very close to the star, but then we have a larger structure farther away. So maybe there's migration between planets. This could be something that we have not explored thus far. We need longer exposure time in order to start having this nicer signal to noise light curves around these white dwarfs. So this is something that we have been proposing for more observations. And that's it. Thank you very much.
Thank you very much, Jesus, for this wonderful talk. Very nice. And okay, for the participants in Zoom, you can raise your hand for doing questions. And Jesus, if you see any question in the room, please go ahead.
We have a question here in the auditorium.
Go on. So, yeah, exactly.
Just wait.
Can you hear me?
Yeah, well,
Actually, I had several questions and just a comment. One on my first question is regarding the spectral energy distributions. It would be great to distinguish between the envelope and scenario against this scenario. I am wondering if you can put again the slides. I am wondering, how do you infer the size of these infrared sets, the size of the structures of about 200 AU and 2000 AU, to say or to claim this is a disk? How you infer it? Because I am worried, because it could be a disk, but also it could be an envelope, the ejected envelope. This is a key point to claim this is a disk.
Yeah. Actually, that's why I wrote debris disks or clouds. Some models require the structure to be spherical, like a shell. And in other cases, it could be a very broad disk. But we haven't done it very carefully. We just did it in order to try to get a fit to the infrared data. But this is something that is not being done properly. And it also depends on how big the structures are, the dust, the composition of the dust, and so it requires more modeling into that sense. But we were only trying to fit the size of the structure. We were not worried, in particular in this paper, we're not worried on the chemistry on this. But this is something that can be explored definitely in the future. Mm-hmm.
Sorry, Mayra, can you approach to Jesus? Not necessary to change the micro, just.
Or she can ask and I can repeat the question also.
Okay, yeah. This.
Con que te lo acerques así.
No, how do you constrain the size of this structure to explain the infrared excess? I guess this is very important to play if this is a disk or a envelope.
Of course. So in cloudy, part of the parameters that you include in the model and you can vary is the the ionizing photon flux from the start, which is or black body model radiation, whatever. And then you start defining, we started by, as I told you, shell. And then we started by varying the inner and the outer shell. And this is what lets you know a little bit about the contribution from the two shells. So as I mentioned, we just did very rough simulations. Cloudy works in 1D. It's very swift for the calculations. So we just vary the inner and the outer radius. And then once you fix the inner radius, which lets you know about the inner part of the disk is this part, the hottest part. And then as you can tell, but not in all cases, we have longer wavelength measurements. Actually, in particular, this is the Helix Nebula, the one on the bottom right. And we were thinking on ALMA data for this, but there's currently ALMA data and they did not detect the structure. So so we don't know what's happening here. Okay. Anybody else here?
We have a question on the chat.
Okay.
I can read it. Does the question is by Mike Credlow. Does the model of the infrared excess, the breeze disk or cloud, also provide the mass estimates of this assumed structure?
For this, you also start. We have to start thinking on filling factors and the real geometry, which we have not done. This was just a swift back at the envelope calculation. So the answer is we haven't estimated any masses for this debris disks or clouds. Mm.
We have a question, Manuel, please go on.
Hello, Jesus, and everybody else. Thank you very much for your talk, very illuminating, and going through all the different stadium of the evolution. I have one question about, we are recently looking at the mass loss rates of the hot Jupiters around the star, namely K star, using the helium triplet line in the near infrared. And this has been really very recent, only a couple of years ago. Have you considered, or anybody have been, whether it is feasible to get any, to measure the helium triplet line of those systems?
We haven't thought about it. We've been using the X-ray as signature of the presence of these Jupiter-like planets, but we haven't thought about any other kind of observations so far, because although I mentioned that there were only 9 of these sources, my student analyzed more than 100 white dwarfs observations. So he took his time, and we also going for the Chandra archive. So this is currently not part of our plan, but of course it will be nice to detect the signatures of the planet in other wavelengths.
You can comment on the possible variation of the
yeah, well, of course. For example, the central star of the Helix Nebula exhibits a variation of the H-alpha line, and some other central stars of planetary nebula also exhibit variation of the H-alpha line, which I guess is by irradiation probably. And but in those cases, there's no signature of a companion. So very likely is due to the presence of planets. Mm-hmm.
Okay, thank you very much. I think it is, well, at least from the point that excitation, we had the ingredient enough, because we had the strong X-ray, which will be excited the helium triple line, the one is in an excited state. So I think it could be useful trying to just a little to back on the envelope calculation about that kind of helium triple observation could be done.
Definitely, yeah. Mm-hmm.
Okay, thank you.
Thanks.
Other questions?
We have a question here.
Okay, go.
About the variability. So I'm just thinking of the geometry of the system. So basically, there is a planet that is like evaporating, and then you have this tail that is the tail of the atmosphere of the planet that is basically accreting on the star. So is this variability due to the thickness of the atmosphere that is evaporating, or to what specifically that you can think?
We haven't explored this, but it might be what we think from the simulations. It might be attributed to different factors. For example, here the disk is, you cannot see, is not homogeneous, or at least we haven't arrived to any self-similar result. It can also be due to self-absorption from the disk. These are only cuts in the plane, so we still need to include the inclination. So maybe these structures are spiraling. Let me just try to. Might be the ones producing the variability. We still need to do this synthetic images of this. These are just the hydrodynamical results, and this is only a cut in the edge on or the pole on plane. This is something we still need to do.
I mean, there is no hypothesis of the orbit.
Initially, what we think is causing the variability is due to the orbit of the planet, but the simulations are showing that the disk is not homogeneous, not too far in the simulation. These simulations are still running in the cluster in UNAM.
Thank you. I had a question regarding these simulations. It seems to me the temperature in this mid-plane high, 10 to the 5, 10 to the 7. I wondered, are you representing the gas or the dust emission? Because the dust is destroyed, the sublimation temperature is around 1 or 2000 AU, but it seems to me that this temperature of the simulation are so high, no?
They're actually high because there's X-rays. Otherwise, we wouldn't have X-rays. X-rays are detected for a gas around above 10 to the 6. If there will be any, you can see here, the highest temperature corresponds to the highest X-ray emissivity. If there's no high dust, we don't have X-ray emission. There's no dust in the simulation, in the simulations. No. It's just gas, yes. So the shock is produced in the disk. So due to viscosity effect and the accretion, the gas gets heat up to temperatures higher than to the 6. And otherwise, we wouldn't have any X-ray emission. The X-ray emission is detected above 5.5, 10 to the 5 Kelvin. Mm-hmm. There's no dust in the simulation. No, in order to include dust, you need to use a double scheme solver, because gas and dust might not be coupled to the radiation. No. Then again, what I said before is that the disk is very small compared to the size of these dusty-rich structures. The disk is almost very close to the white dwarf, and this infrared emission that we detect, they're farther away, so they're not resolved in the simulations. That's why it's not included here.
We have a question here.
Okay.
Eva, please go on.
Hi, Jesus.
Hola.
Nice talk. Hola. Very nice talk. My question is regarding the compatibility of, this high rate of detections of planetary systems. Let's assume that there are detections, right? That you have 6 planetary systems around a planetary nebula. If you compare with the rate of detections around white dwarfs, then this rate is very high. In order to get the planet close to a white dwarf, to explain pollution, to explain the presence of the disks, or the Keplerian velocities of the disks that you get in the white dwarfs, then you have to assume that for example, the scenario that works better is if you assume that you have multiple systems and they get destabilized when the heavy mass loss takes place. But this mechanism takes time. It will not happen in the short time of the planetary nebula phase. And before that, you have the AGB phase, which is going to basically shallow every planetary system that you are going to have nearby. So my question is, how compatible is this high rate of detections or putative detections with what you get in the white dwarfs?
Actually, these are detections in white dwarfs. These are not central stars of planetary nebulae.
With these temperatures, I mean, they're very hot.
These are white dwarfs, yes. White dwarfs with very,
yeah,
very
well, the
high...
central stars of planetary nebula are white dwarfs. But I mean, my point is that they are very hot. They are very early in evolution. And for the mechanism of the instability to take place, you need time.
Okay, yeah, well, the Helix Nebula, which is, so in this image that I'm showing, the only white dwarf that is a central star of a planetary nebula is the one on the right bottom panel, which is the Helix Nebula. So far, people don't understand why the properties or the X-ray emission. We propose that it's very close or similar to other white dwarfs that do not have planetary nebula associated, and it has very similar X-ray properties, which we explain with the presence of a planet. I don't know nothing about on the timescales that a planet should survive, but at least these are the best candidates to explain the X-ray emission. I definitely ignored anything you mentioned, but what we see is that we have this excess. We don't have any stellar companion, so at least a substellar object should be producing this excess. Either most likely it's a Jupiter-like planet, and it could be also, brown dwarf. Yeah, sorry for not having the answer. Okay. You see.
Okay. Now my point is that it has to be consistent with all the body of observations and simulations that we have been doing on white dwarfs and evolution of planetary systems. So I mean, this is very exciting. I mean, if it is true that it is really a planetary companion, it's very exciting. But then you need to explain how is there and how it gets there, and the mechanisms that operate. I mean, for example, in instabilities on the white dwarf, they operate later. I mean, they need more time than the ones that you have. I mean, at least with effective temperatures that you have there.
Yes,
that would be a problem for that.
All of those effects, for example, migration. I have no idea on how it comes to occur. For example, let's say, how can you have this very massive gaseous planets very close to the star and then this debris disk further away? I do not understand or not trying to understand the current configuration. This is just the evidence on the X-rays and the infrared that we have, but we haven't done any further investigation into this.
Yeah. Okay, thank you.
Thank you, Eva. More questions for Jesus?
We don't have any questions here. People are afraid of me.
Okay, in none, we can end this wonderful talk. And just one more question: how long you will be in Granada, Jesus?
I will be here until the 31st of May. So still 1 month, a little bit more than 1 month.
Okay, thank you very much.
You're welcome. Thank you.